In this video, I'm going to discuss the log-log technique for finding out what is the power function behind a set of data. So this is something maybe you haven't seen before. I actually first saw this technique in an advanced chemistry course where they were doing some analysis over thermodynamics. In this case, basically the idea is the following. Let's suppose for a moment that I have this data, right, that's supposed to be represented by some unknown function, right, like that table we talked about when we benchmarked ThreeSum. Well, one thing I could do if I suspect it's a power function is basically take the logs of the two kind of pieces of the pieces of data, right? So the pieces of data are paired. There's problem size and time. Take log of both those, right? So basically plot log time versus log problem size. And what we get there basically is this fact, I suppose, that on a log-log plot, if I have a linear function, then that implies that there is a power function that models the kind of original stuff, right? Just the raw problem size and the raw running time, right? Instead of the logs of it. And so this is basically a way that we can easily look at our data and try to tell if it looks something like a power function. Power functions in general are going to be very common in program analysis because whenever we have nested loops, it'll look like a power function. So one loop, right, is basically going to look like something like n, right, power of 1. Two nested loops can look like 2. Three nested loops can look like 3, right? I should say they're n to the third. So basically our power functions are very common in terms of what we see from programs that use loops, which again are very common, right? Everybody uses loops. And so the idea here, right, is if we do this plot, right, this log-log plot, I can instantly see whether or not that assumption is correct, whether or not my program is looking like something that uses nested loops, just by seeing whether or not there's a linear function that appears. So over here, if we look at the plot that I've made, right, we can basically see that there is this sort of linear function that occurs. Right, it's not going to be perfect. Our benchmark data is always a little noisy, but in general, I can look at that and say, oh yeah, it's linear. So for sure, I know that this thing is going to be a power function. And then once I've kind of done that, then I can actually look at the values there and try to use them to figure out what is the function that would model this data. So provided that I'm doing a log-log plot, basically, I have this equation here, right, of just a line. And I already said, oh, hey, if the data looks like a line in the log-log plot, that implies it's a power function. So we can imagine actually doing regression on the log-log data to learn what exactly is that line, right? Or maybe you can even do it yourself. Even if you have just a few points, right, you can maybe figure out what exactly is the function that fits that. So if you go and get the function for this data, right, in this log-log view, it'll look something like this, right? We have our log of f of n, right, basically our time, equals b times log of n, right? That's our log of our problem size plus c, right? That's how a linear function looks. And so our data basically will fit that, right? Our logs, right, are basically forcing our data, right, to look like a line and give us a little bit of a simpler form, right, rather than some polynomial, right, that has some coefficients and powers, etc. Just make it look like a simple line. And so if we have this plot, this log-log plot, basically what happens is that, well, I'm looking at a line, so a line has a slope and it has an intercept, this b and c value. And so the b and c values, right, are over here. Now what I can basically do is rearrange this, right? Rearrange this algebraically by taking powers on stuff. And from that, basically get back an expression that models my f of n, or in this case, I'm going to use t of n because really it's predicting time, based on b and c, right? The values that we can easily recover from this linear equation on this graph. So over here, right, I have that formula, t of n equal a n to the b. So this is now basically my t of n, my function that predicts the amount of time based off of those variables, right? A and c. Really in here I've introduced something called b as well, but you'll notice that b is defined, A is defined as being equal to 2 to the c, right? So this little variable over here is defined like this. And so basically, right, this I can basically get algebraically. You can try doing it offline if you want. But once I have this, or once I know this, right, I can basically substitute in my known values for c, and then compute the value of a from b, and then I have my coefficient of my power on n. So if I were to do that, right, substitute in these values. So this is coming from the chart, right, and it's really easy to find these things. These get substituted in, right, so this gets substituted in over here, right, 2 to the negative 33, ends up giving me this 1.006, and then the 3.999 basically becomes our power on n. All right, so at the end of the day, I have this last line here. my t to the n equals all this stuff, right? So that is basically my model for this data based on a log-log plot. So overall, this is an alternative to general regression. The hope is that it's easy for you to do a log-log plot. You don't need to go through all these regression steps, and you can at least determine whether or not it's based on a power function, meaning is it based on loops or not. So this is one method. We'll take another look at another method in a few videos.